Hi everyone, welcome to topic 7.2, One-Way ANOVA. The learning objectives are as follows. First we will look at how and why we conduct one-way ANOVAs. Next we will discuss hypotheses and assumption testing. Lastly we will talk about post hoc testing and in particular Tukey's honestly significant difference test. Okay, so with ANOVA or analysis of variance, it's important to understand that this is a continuation of t-testing, as we are still comparing the differences between means. In particular, the one-way ANOVA is an extension of the independent samples t-test where we looked at two means, but with ANOVA we're comparing or testing more than two population means. An example might be whether there is a significant difference in average sales performance between teams A, B, C, D and E. Okay, so the assumptions for the test, these are the same as the independent samples t-test. The populations are normally distributed, the population standard deviations are unknown but assumed equal, and the groups are independent. Okay, so the hypotheses for the one-way ANOVA are as follows. HO, the null hypothesis, mu is mu1 equal mu2 equal mu3 and so on. Look, this depends on how many population means we are comparing. The alternative hypothesis is not all the means are equal. Please note here, we are not saying that all the means are different, we are just saying that not all the means are equal, or at least two means differ. Okay, so here you can see the hypotheses on the slide. On the left is the null hypothesis where we are saying all the means are equal. On the right is the alternative hypothesis. In this case, populations 1 and 2 may not differ from each other, but may be significantly different from populations 3 and 4, which are not different to each other. This is an example, and you can imagine all the different iterations in terms of the differences that we're testing. Okay, so for the one-way ANOVA, and the reason it's called analysis of variance, is that we calculate the variability between the groups and the variability within the groups. The ratio is then calculated, and this is known as the F-statistic. To understand how the F-statistic is calculated, we first need to understand variation. The total variation in our data set, SST, sum of squares total, is made up of between group variation and within group variation. The between group variation is also known as variation due to the factor, sum of squares treatment, sum of squares between, sum of squares among, sum of squares explained, or among group variation. Look, I just mentioned this as different textbooks will refer to different things, but it is all between group variation. Now, within group variation is also known as variation due to random sampling, sum of squares within, sum of squares error, and sum of squares unexplained. Okay, so here is some data to help us understand this. First, SST, sum of squares total, is the variation between each data point and X bar bar, which is the mean of the means, or otherwise known as the grand mean. As you can see, Group 1 has 3 data points, Group 2 has 4 data points, and Group 3 has 4 data points. The SST is calculated with each data point, subtract the X bar bar, the grand mean, and then we square each of these data points to avoid cancelling out positive and negative values. These values are then added together to form the SST, sum of squares total. Okay, so now here we're calculating the between group variation, or SSTR, sum of squares treatment. So you can see that each sample mean is subtracted from the grand mean. These values are then squared so that they're all positive, and then multiplied by the sample size, and lastly all the values are added together. This figure tells us the variation between the groups. So now here we are calculating the within group variation, SSW. You can see that each data point is subtracted from its sample mean, and then the values are squared, and lastly the values are added together. This final figure, SSW, sum of squares within, tells us the variation within the groups. Okay, so now let's look at an example to further understand ANOVA, or one-way ANOVA. Here we're wanting to test whether the average cost savings using public transport differ between cities. The null and alternative hypotheses are presented on the slide for you. Now we need to calculate the F-statistic, well Excel does, and the F-critical value. You can see that the degrees of freedom are a little bit more complicated here. DF1 is calculated as C minus 1, so C, the number of groups, in this case 4, minus 1, so DF1, degrees of freedom 1, is 3 degrees of freedom. DF2 is the total sample size, subtract the number of groups. So to get to DF2, we go 24, subtract 4, which gives us 20 degrees of freedom. Now we need to use this information to work out our F-critical value. So take a look at your F-distribution table at the back of your textbook. It's table 4, which starts on page 736. We use DF1 and DF2 as coordinates to reveal the F-critical value of 3.10. Check to see if you can find this value. Okay, now before we go to the next slide, I want you to consider the shape of the F-distribution. It's quite different to the T. So take a look at the top of page 736. Here you can see that there's only one rejection region and it's in the upper tail. Look, this makes sense when you apply logic to the F-statistic calculation. Have a look on the slide. The numerator in the F-statistic calculation is the mean sum of treatment, so the between group variation, or the SSTR, sum of squares treatment, divided by the DF1, the degrees of freedom 1. The denominator is the F-statistic in the F-statistic calculation is the mean square error. So this is the sum of square error divided by DF2. So have a think about that for a moment. The mean between group variation divided by the mean within group variation. So think about which number will always be larger, between group variation or within group variation. Yes, you are right if you are thinking between group variation. By the very nature of groups, they should have similarities, and so therefore we expect that within group to be smaller value than between group. So if we expect a numerator to always be larger than a denominator, which is in the case of the F-statistic, we will always see this as a positive number. Well done if you figured that out. Okay, so lucky you, Excel computes this output for you. The table is the common way to present the ANOVA output. In the previous slides, I've shown you how to calculate these figures. As you can see in the table, the second column with the heading SS, sum of squares, shows us the sum of squares between, the sum of squares within, and the total sum of squares. The next column, headed DF for degrees of freedom, shows us the DF1, the DF2, and the total degrees of freedom. The next column, MS, mean square, shows the mean squares between and the mean squares within. Please note these values are calculated as the SS, the sum of squares, divide the degrees of freedom. The F-statistic is presented in the next column, and this is calculated as the mean square between divide the mean square within. The associated p-value is presented next. The last column contains the F-critical value. As you can see, the p-value is less than the alpha of 0.05, so we reject HO. Or using the critical value approach, we can see that the F-statistic is beyond the F-critical value, so we reject HO. We can therefore conclude that not all the means are equal. However, we don't know if all 4 cities differ, or if one differs to the other 3, and so on. To determine where the differences lie, we need to conduct multiple comparisons. To perform the multiple comparisons for this unit, we will employ Tukey's Honestly Significant Difference method, HSD method. Here is the formula for calculating the confidence interval for the Tukey HSD procedure. Although it looks complicated, have a closer look, and you will see that these values are all given except for the Q statistic, which we find in Table 5, which starts on page 740 of your textbook. To find the Q statistic, you need to look up C, the number of groups, and N takes C, which is the sample size, subtract the number of groups. Let's work through our example to understand how to calculate this and how to interpret the results. Here are the sample statistics for the 4 cities. We will need these values for our calculations. Okay, so on this slide I'm presenting the workings for the Tukey test. Please note your textbook works through this same data using Fisher's LSD, least significant difference method. This test yields slightly different results, and as the book acknowledges, the Tukey's Honestly Significant Difference procedure is considered a better method compared with Fisher's LSD method, as the Fisher's method inflates type 1 error, so therefore we're going to use the Tukey test. Here you can see on the slide I'm calculating the differences between City 1, Boston, and City 2, New York. The Q statistic of 3.96 was obtained from Table 5, page 740 of your textbook. Tukey's HSD method produces a confidence interval, and as you know from the estimation seminar, if this confidence interval contains 0, the difference is not significant. As shown, the difference between Boston and New York is not significantly different, but all other comparisons are significantly different. In conclusion, for this example, we can say that apart from New York and Boston, there is evidence of a significant difference in terms of the average cost saving from using public transport between the cities of Boston and San Francisco, Boston and Chicago, New York and San Francisco, New York and Chicago, and San Francisco and Chicago. Note the means are contained on the slide so that you can see when comparing means which mean is higher. Okay, that's one way and over.